Hello everybody, my name is Ethan. Welcome back to the channel where today we are going to be going back into our world of machine learning on the machine learning course on Codecademy. In the previous video, we finished one of the longest chapters of the actual unit of machine learning fundamentals. It's hard to break it down into chapters, sections. I don't really know what to call it. I'm going to just call it the main subdivision chapters, and then these just sections. So I guess we're finishing one of the longest sections, which was this one right here, Supervised Learning 1. Had a lot of stuff. So we finished that last episode, and we are now going to just go right into feature selection models. And I'm going to stop wasting your time and get right into it with the introduction to feature selection models. So we're going to learn about the pros and cons. Let's talk about the introduction and motivation. Imagine you want to build a machine learning model for predicting the presence of a disease. You have a data set of patient records containing hundreds of different metrics, from demographic characteristics to medical test results to past treatment history. While having access to so many data points is always a good starting point, you most likely would not want to use all of the available features to construct your model, as many of them can be redundant or irrelevant, and would only serve to contribute unnecessary noise. Instead, a more effective approach is to select only a subset of relevant predictive features to use in your model. This process is known as feature selection. Feature selection is an important step in the machine learning pipeline, and when done right, can optimize the performance and predictive power of your model. The goal is to improve the model's accuracy and efficiency by eliminating extraneous variables that do not contribute any useful information. In addition, simplifying the model through feature selection not only makes the results more easily interpretable, but also reduces the time and resources required to run the model. So there are three broad categories of feature selection that we're going to discuss in this article: filter methods, wrapper methods, and embedded methods. So feature selection models, filter methods. Filter methods are the simplest type of feature selection model or method. They work by filtering features prior to model building based on some criteria. Advantages: they are computationally inexpensive since they do not involve testing the subsetted features using a model. They can work for any type of machine learning model. Disadvantages: it is more difficult to take multivariate relationships into account because we're not evaluating model performance. For example, a variable might not have much predictive power on its own, but it can be informative when combined with other variables. And another disadvantage: they're not tailored towards specific types of models. Examples: variance thresholds, correlation, and mutual information. Number two of our methods is going to be wrapper methods. Wrapper methods involve fitting a model and evaluating its performance for a particular subset of features. They work by using a search algorithm to find a combination of features that can optimize the performance of a given model. Advantages: they can determine the optimal set of features that produce the best results for a specific machine learning problem. They can better account for multivariate relationships because model performance is evaluated. Now, disadvantages: they are computationally expensive because the model needs to be refitted for each feature set being tested. Examples: forward, backward, bidirectional sequence feature selection, and recursive feature elimination. Finally, embedded methods. Embedded methods also involve building and evaluating models for different feature subsets, but their feature selection process happens at the same time as their model fitting step. So it's very similar to the previous one, wrapper methods, but a little bit different because our feature selection process happens at the exact same time. Advantages: like wrapper methods, they can optimize the feature set for a particular model and account for multivariate relationships, but they're also generally less computationally expensive because the feature selection happens during model training. Examples: regularization, i.e. lasso and ridge regression, and tree-based feature importance. Conclusion: when it comes to the number of features for your model, to keep for your model, more is not always better. It's worth being selective about which features to retain in order to maximize performance and reduce noise. Therefore, finding and implementing the right feature selection method is a key part of developing an effective and reliable model. Okay, we're going to go into filter methods first. So we kind of introduced the idea of these three separate methods: the filter method, the wrapper method, and the embedded method. So we got those three types there. We're going to go a little bit more in depth After we introduce them, we're going to start with filter methods. So learn about the different filter methods for evaluating and selecting features. I assume there's a bunch of different filter methods. So introduction. Filter methods are a type of feature selection method that works by selecting features based on some criteria prior to building the model. Because they don't involve actually testing the subsetted features using a model, they're computationally inexpensive and flexible to use for any type of machine learning algorithm. This makes filter methods an efficient initial step for narrowing down the pool of features to only the most relevant predictive ones. There are many different filter methods that can be used for evaluating and selecting features. In this article, we will use variance thresholds, correlation, and mutual information to rank and select the top features. To demonstrate how these methods work in Python, we'll use the feature selection module from scikit-learn as well as the pandas library. All right, let's get into this example data set here. Let's suppose we have the following data set containing information on a class of middle school students. So we're going to import pandas, and we're going to set it equal to this data frame right here. If we look, it looks a little bit something like that. Our goal is to use the data to predict how well each student will perform on the exam. Thus, our target variable is exam score, and the remaining 6 variables are our features. We'll prepare the data by separating the features matrix x and the target vector y. So we'll do that by using the command drop. We'll drop the exam score, and we'll end up with a data frame containing just the 6 feature variables, right? In this case, though, if we just want to select the 1, we'll take y is equal to the column of exam score, because that is the variable that we are trying to predict or guess on, right? Variance threshold. One of the most basic filter method is to use variance threshold to remove any features that have little to no variation in their values. This is because features with low variance do not contribute much information to a model. Since variance can only be calculated on numeric values, this method only works on quantitative features. That said, we may also want to remove categorical features for which all or a majority of the values are the same. To do that, we would need to dummy code the categorical variables first, but we won't demonstrate that here. In our example dataset, edu goal is the only feature that is non-numeric. We can use the .drop method to remove it from our dataset and store the remaining numeric features in x numeric, right? So educational goal, if we go back up here, educational goal is a categorical variable. It's either bachelor's, master's, or PhD, possibly also something that's a little bit less, I could say. But let's continue here. We've dropped both the exam score column and the edu column. So now we only have 5 features to deal with. Now we're going to be able to use the variance threshold class from the scikit-learn to help remove the low variance features from xnum. By default, it drops all features with 0 variance, but we can adjust the threshold during class instantiation using the threshold parameter if we want to allow some variation. The .fit transform method returns the filtered features as a numpy array, or numpy array, not numpy, sorry. So we create a selector, we create a variable named selector that is a variance threshold object, and we're going to say that 0 is the default. So when we put this in, we're just specifying that it's the same as the default argument. Don't actually necessarily have to put this comment in here, or not the comment, the highlighted piece of text that I've highlighted there. But there is the code we want to do from sklearn.feature selection import variance threshold. First, we'll fit transform the data. We'll get that output. And as we can see, grade level was removed because there is no variation in its values. All students are 8th graders. Since this data is the same across the board, a student's grade level will not be able to provide any useful predictive information about their exam score, so it makes sense to drop grade level as a feature. Something to note is that loading datasets with scikit-learn generally works with numpy arrays internally, hence the output of .fit transform. However, the methods can also accept other data types that can be converted to numpy arrays, such as Python lists or pandas data frames, like the xnum we used. From a human perspective, one downside of working with numpy arrays as compared to pandas data frame is that we lose information like column headings, making the data harder to visually inspect. So in this case, we can see that there's only 4 columns here, and we have to go and kind of look and see which one got dropped. It looks like the last one got dropped because they're all 8s, and we don't see all 8s here, so I ended up dropping that data. Luckily, variance threshold offers another method called .getSupport that can return indices of the selected features, which we can use to manually subset our numeric features data frame. Boom, boom. A lot of interesting stuff there. Perfect. All right, finally we obtain our entire features data frame, including the categorical column edu goal. We could do this, right? And that prints out this nice big piece of text, right? All right, Pearson's correlation. Another type of filter method involves finding the correlation between variables. In particular, the Pearson's correlation coefficient is useful for measuring the linear relationship between 2 numeric continuous variables. A coefficient close to 1 represents a positive correlation, -1 represents a negative correlation, and 0 represents no correlation. Like variance, Pearson's correlation coefficient cannot be calculated for categorical variables, although there is a related point biserial correlation coefficient that can be computed when one variable is dichotomous. We won't focus on that here. I hope I'm saying that. Dichotomous. Uh-oh. Let's see.
Dichotomous.
Oh my god, I'm so good. Dichotomous. Very nice. Correlation between features. When when 2 features are highly correlated with one another, then keeping just one to be used in the model will be enough. Otherwise, they provide duplicate information. The second variable would only be redundant and serve to contribute unnecessary noise. To determine which variables are correlated with one another, we can use the .core method from pandas to find the correlation coefficient between each of the pair of numeric features and the data frame. By default, .core computes the Pearson's correlation coefficient, but alternative methods can be specified using the method parameter. We can visualize the resulting correlation matrix using a heat map. So if we import Seaborn as SNS, we can use an SNS heat map using our matrix here. A couple of different things right there, and then we are able to show it and see this. Let me just check and see where we are within this. We're going to go through wrapper methods as well, so that's fine. All right. We're going to define high correlation as having a coefficient of greater than 0.7 or less than -0.7. We can loop through the correlation matrix to identify the correlation highly correlated variables. So this would help us do that. Our output would be this right here. As seen, hours TV appears to be highly negatively correlated with hours studied. A student who watches a lot of TV tends to spend fewer hours studying, and vice versa. This is because they provide redundant information. We can choose to remove one of these 2 variables. To decide which one, we can look at their correlation with the targeted variable, and then remove the one less associated with that target. This is explored in the next section. Correlation between feature and target. As mentioned, the second way correlation can be used is to determine if there is a relationship between feature and the target variable. In the case of Pearson's correlation, this is especially useful if we tend to fit a linear model, which assumes a linear relationship between the target and predictor variables. If a feature is not very correlated with the target variable, such as having a coefficient between -3 or 0.3 and -1 or -0.3, then it may not be very predictive and can be potentially filtered out. We can use the same .core method as seen previously to obtain the correlation between the target variable and the rest of the features. First, we'll need to create a new data frame containing the numeric features with the exam score column. Then we can generate a correlation matrix and isolate the column corresponding to the target variable to see how strongly each feature is compared with it. Right there. Prints this. As seen, our study is positively correlated with exam score and hours TV is negatively correlated with it. It makes sense that our study and hours TV would be negatively correlated with each other, as we saw earlier, and just one of those features would suffice for predicting exam score. Since hours TV has a stronger connection with the target variable, let's remove hours TV or hours study has a stronger correlation. We're going to drop this column instead. The other two features, hours sleep and height centimeter, both do not seem to be correlated with exam scores, suggesting that they would not be very good predictors. We could potentially remove either or both of them as being uninformative. But before we do that, it's a good idea to use other methods to double check that the features truly are not predictive. We will do that in the next section by using mutual information to see if there are any nonlinear associations between the features. The feature returns a F statistic in the first array and the p-value in the second. As seen, the result is consistent with what we have observed in the correlation matrix. The stronger the correlation, either positive or negative, between the feature and target, the higher the corresponding F statistic and lower the p-value. For example, among all features, our study has the largest correlation coefficient, 0.905, highest F statistic, 3.61 to the e to the 1 power, and lowest p-value. Mutual information. The final filter method we'll look at is using mutual information to rank and select the top features. Mutual information is a measure of dependence between two variables and can be used to gauge how much a feature contributes to the prediction of the target variable. It is similar to Pearson's correlation, but not limited to detecting linear associations. This makes mutual information useful for more flexible models where linear functional form is not assumed. Another advantage of mutual information is that it also works on discrete features or target, unlike correlation, although categorical variables need to be numerically encoded first. In our example, we can encode the EDU goal using label encode from scikit-learn's pre-processing module. So we'll say we'll import the label encoder, do LE is equal to label encoder, create a copy of X for encoded version, do that, and then print the encoded. Now we can compute the mutual information between each feature and exam score using mutual info regression. This function is used because our target variable is continuous, but if we had a discrete target variable, we would use mutual info class if, and we specify random state in the function in order to obtain reproducible results. The estimated mutual information between each feature and the target feature is returned in a NumPy array, where each feature is a non-negative number. The higher the value, the more predictive the power is assumed. However, we're missing one more important piece here. Earlier, even though we encoded EDU goal to be numeric, that does not mean it should be treated as a continuous variable. In other words, the values of EDU goal are still discrete and should be interpreted as such. If we plot EDU goal against exam score on a graph, we can clearly see the steps between the values of EDU goal. As you can see right here, here. In order to properly calculate the mutual information, we are going to tell mutual info regression which features are discrete by providing their index positions using the discrete features parameter. Compared to earlier results, we now get a mutual information between the EDU goal and the target variable once it is correctly interpreted as a discrete feature. From the features, we can also see that there is a zero mutual information between height centimeter and exam score, suggesting that these variables are largely independent. This is consistent with what we saw earlier with Pearson's correlation, where the correlation coefficient between them is close to zero as well. What is interesting is to note is that the mutual information between sleep hours and exam score is positive value, even though their Pearson correlation coefficient is zero. The answer becomes more clear when we plot a relationship between hours sleep and exam score. As seen, there does seem to be some association with the variables on only one layer, but why is detected using mutual information but not Pearson's correlation coefficient? Finally, let's look at the select K best from scikit-learn to help pick out the top K features with the highest ranked scores. In our case, we're looking to select features that share the most mutual information with the target variable. When we instantiate select K best. We'll specify which scoring function to use and how many top features to select. But because we want to specify additional arguments besides x and y, we'll need the help of partial function from Python's built-in functools module. Then the fit transform method will return the filtered features as a numpy array. Perfect. As seen above, we selected the top 3 features based on mutual information, thus dropping height centimeter like variance threshold, select K best. Also offers the .get support method that returns the indices of the selected features, so we could subset our original features data frame. Conclusion. In our example dataset, we started out with 6 features for predicting the exam score of students. Using various filter methods, we narrowed that set down just to the top most relevant and informative ones. First, we eliminated grade level because it had 0 variance and would contribute nothing to the model. Then we dropped hours TV since it's highly correlated with hours study and therefore redundant. Lastly, we filtered out height centimeter based on mutual information, which suggested that it does not have any meaningful association with the target variable, linear or otherwise. And would not have been very predictive, right? That was a lot we were able to accomplish using filter methods, being the most simple type of feature selection method. They sure do pack a lot of power, nor potential. I said they pack a lot of power. They said they do not lack power. All right, introduction to wrapper methods. Machine learning problems often involve datasets with many features. Some of those features might be very important for a specific machine learning model. Other features might be irrelevant. Given a feature set and a model, we would like to be able to distinguish between important and unimportant features, or even unimportant combinations of features. Wrapper methods do exactly that. A wrapper method for feature selection is an algorithm that selects features by evaluating the performance of a machine learning model on different subsets of features. These algorithms add or remove features one at a time based on how useful those features are to the model. Wrapper methods have some advantages over filter methods. The main advantage is the wrapper methods evaluate features based on their performance with a specific model. Filter methods, on the other hand, can't kind of tell how important a feature is to a model. Another upside of a wrapper method is that they take into account relationships between features. Sometimes certain features aren't as useful on their own, but instead perform well only when combined with other features. Since wrapper methods test subsets of features, they can account for those situations. This lesson will explain 5 different wrapper methods: sequential forward selection, sequential backwards selection, sequential floating forward selection, sequential backward floating selection, and recursive feature elimination. You'll learn how to implement these algorithms in Python. Before we get started, take a look at the dataset you'll go throughout this lesson. The data in the workspace was taken from the UCI machine learning repository. The outcome variables classification is a 1 if a patient has breast cancer, 2 if not. The features are age, BMI, as in body mass index, glucose, insulin, HOMA, which is homeostatic model assessment, a measurement of insulin resistance, as well as 4 different protein levels, leptin, and some that I don't want to try and pronounce. First, it wants us to uncomment this and take a look at the data. What are some of the pros and cons of having this many features? So again, we have quite a few features within this data set. We're going to see if we can filter some of these out using some wrapper methods to get a better idea of what helps in regression. Setting up a logistic regression model. Before we can use a wrapper method, we need to specify a machine learning model. We'll train a logistic regression model on the health data and see how well it performs. We'll prepare the data by splitting it into a pandas data frame, X, and a pandas series, Y. X will contain the observations of independent variables, and Y will contain the observations of the dependent variable. Here's an example of how to do this. The FIRE dataset was taken below from the UCI machine learning repository and cleaned for our analysis. Features the temperature, RH, WS, rain, DMC, and FWI columns. The final column, classes, contains a 1 if there was a forest fire in a specific location on a given day and 0 if not. So we can create a logistic regression model and fit it to X and Y with scikit-learn using the following code. So it wants me to do that. Looks like it has already done some of the work, but I am going to have to fit the model to X and Y. Logistic regression models give a probability that an observation belongs to a category. In the fire data set, probabilities greater than 0.5 are considered predictions that there is a fire, and probabilities less than 0.5 are considered predictions that there is no fire. In the health data set, probabilities that greater than 0.5 are considered predictions that a patient has breast cancer. The accuracy of a logistic regression model is the percentage of correct predictions that it makes on a testing set. In scikit-learn, you can check the accuracy of a model with the .score method, and the output does this. So use the fit method on LR, and if I click run, I've entered that in already. And it wants me to do the print score method, so we'll do lr.score with X and Y as arguments. Excuse me. This one looks like it's about 80% accurate, which is pretty good. Sequential forward selection. Now that we have a specific machine learning model, we can use wrapper method to choose a smaller feature subset. Sequential forward selection is a wrapper method that builds a feature set by starting with no features and then adding one feature at a time until a desired number of features is reached. In the first step, the algorithm will train and test a model using only one feature at a time. The algorithm keeps that feature that performs best. In each subsequent step, the algorithm will test the model on each possible new feature addition. Whichever feature improves the model performance the most is then added to the feature subset. This process stops once we have the desired number of features. Let's say we want to use 3 features, and we have 5 features to choose from: age, height, weight, blood pressure, and resting heart rate. Sequential forward selection will train your machine learning model on 5 different feature subsets, 1 for each feature. If the model performs best on the subset age, the algorithm will then train and test the model on the following 4 subsets: age and height, age and weight, age and blood pressure, age and resting heart rate. If the model performs best on age and resting heart rate, then the model will test the model on the next following 3, which will do age, height, and resting heart rate, age, weight, and resting heart rate, age, blood pressure, and resting heart rate. If it performs well, I guess the best on age, weight, and resting heart rate, I'll stop their algorithm and use that feature set. Sequential forward selection is a greedy algorithm. Instead of checking every possible feature by brute force, it adds whatever feature gives the best immediate performance gain. If you use sequential forward selection to add a 4th feature to the dataset, age, weight, resting heart rate, you'll see that in the preceding example, what 2 feature sets would the algorithm test? Create sets called set 1 and set 2 that contain the appropriate features. For example, if the answer was resting heart rate and weight, you would type that. So it wants us to create 2 set variables that have the values of add a 4th feature to the resting heart rate that contain appropriate features. We're adding a 4th feature to the set. What 2 would the algorithm? Oh, test in the set. I see. So instead of ending at 4, we want to end at age, comma. In set 1, it's going to test between. So first it found age, then age and resting heart rate, then age and weight and resting heart rate. So the 2 left that we have to train on is height and blood pressure. So we'll do blood pressure and then weight, and then finally to end this one out we'll go with the resting heart rate. Finally, in set 2, I'm going to do a little bit of copy and pasting here just because it's going to be very, very similar to set 1, except this blood pressure is going to be swapped out for height. Perfect. Sequential forward selection with MLX-tend. Recall from a previous exercise that the logistic regression model was about 80.2% accurate at preceding if a patient had breast cancer. But There were 9 different features. Are all of those features necessary, or is it possible that the model could make accurate predictions with fewer features? That would make the model easier to understand and could simplify diagnosis. We will use the SFS class from Python's MLX10 library to implement sequential forward selection and choose a subset of just 3 features for the logistic regression model that we used earlier. So we're setting up our parameters and fitting it to the features X and outcome Y. Excuse me. The first parameter is the name of the model that you're using. In the previous example or exercise, we used the logistic regression model LR. So we have LR here. The parameter K features determining features the algorithm will select. We're saying 3 in this case. Forward equal true and floating equal false ensure that we're using sequential forward selection. So forward equals true means it's forward, and sequential means, I suppose, floating equals false. Scoring determines how the algorithm will evaluate each feature subset. It's often okay to use the default feature none because MLX10 will automatically use a metric that is suitable for whatever scikit-learn model you are using. For this lesson, we'll set it to accuracy. CV allows you to do k-fold cross-value validation. We'll leave it at 0 for this lesson and only evaluate performance on the training set. We'll see what features were selected in the next exercise. For now, we want to fit the SFS model. Use MLX10 to create an SFS object called SFS. Set it to 3, select 3 features, and make sure that you're using forward and floating arguments to ensure that you're using sequential forward selection, and also setting scoring equal accuracy and CV equal to 0. So it wants us to create this object called SFS, and we're going to set it equal to the SFS class. We're going to call it, did it want us to call it anything? I guess we're just going to call it the linear regression. It's already right there. We're going to say that we have K features equal to 3 features. We'll then say forward is equal to true. We'll say that floating is equal to false. Scoring is equal to accuracy. And CV is equal to 0. Next, it's going to want us to use the .fit method on SFS and fit it to our X and Y variables. Perfect. Evaluating the results of a sequential forward selection. The SFS object that you fit in the previous exercise contains information about the sequential forward selection that was applied in your feature set. The subsets attribute allows you to see much of the information, including which feature was chosen at each step and the model's accuracy after each feature selection addition. SFS subset is a dictionary. It looks something like this. The keys in the dictionary are the numbers of features at each step in the sequential forward selection algorithm, and the values in the dictionary are dictionaries with information about the feature set at each step. Average score is the accuracy of the model with the specified number of features. In this particular example, the model had an accuracy of about 93.9% after the feature FWI was added. The accuracy was improved to about 97.5% after a second feature, DMC, was added. Once 3 features were added, the accuracy improved to about 98.0%. You can use this dictionary to easily get a tuple of chosen features or the accuracy of the model after any step. We got a tuple here of feature names after 5 features are added. This outputs this. Print the accuracy of the model after 5 features are added. This outputs this. The MLX10 library also makes it easy to visualize how the accuracy of the model changes as sequential forward selection adds features. You can use the code plot SFS and then put sfs.getMetricDict to create a matplotlib figure that plots the model's performance as a function of the number of features used. That's how you would do it there. As you can see, it goes up. Use the .subsets attribute of SFS to print a tuple that contains the names of the features. So we're going to say print sfs dot subsets underscore, and we're going to go up and we want to select the features in the previous exercise that we chose 3 features. So we want to choose the 3 features. It's going to give me a big old error. Did I do it right? Yeah, I did. To print the accuracy of the model with these 3 features after doing sequential forward selection. So to do that, we're going to go up and do this. I know, actually, we'll print. Oh, I see. So it wants me to actually print feature names. I see. This makes sense. And then we can also print sfs.subsets with the index of 3 because we have 3 selections. And then finally, we'll use that average score to also print what our score looks like. So that makes sense. Age, glucose, insulin, 76%. Use plot sfs.getMetricDict to plot the accuracy of a function. Remember to show your plot. So we'll plot it doing plot sfs with sfs dot and then get metric dict, and it has that. We can do plt.show. So we end up gaining quite a bit. Very nice, nearly 3% if we add more features. All right, sequential backward selection with MLX10. I'm actually going to call it video here. It's getting already a little bit longer than I wanted it to be. So we'll pick up where we left off in the next video. I want to thank you so much all for watching. If you did enjoy the video, please be sure to give it a like, subscribe, and I will see you in the next one. Peace out.